Hi, friends. It's Ben again, broadcasting from my back porch, where we've begun to suspect that summer might be over. Or so. This is a video for Calc 3. We are taking a look at the notion of iterated integrals. I believe that's section 15.1 in your textbook. So with regard to this, I'm going to give you all a bit of a confession that to me, 15.1 and 15.2 are not two different sections. They are the same section with just a slightly different emphasis on it. So I've got two videos for you, but those videos may seem a little bit alike. So bear with me on that part. So when we're talking about iterated integrals, we are talking about what's referred to as double integrals. They're the same thing. But when you talk about a double integral in the theoretical end of things, you're talking about a domain that is two-dimensional. Whereas with an iterated integral, you are evaluating the double integral by integrating twice. So y'all have had Calc 1 and Calc 2, so not only do you understand integration, you are masters of integration because you have done the integration techniques that come up in Calc 2. And it can get pretty hairy, you know? So with what we're talking about, it's really just that, okay? With one change. And you have to listen to me on this. And for those of you who don't listen to me, you will just get some problems with 0 credit on them. Sorry. There is no such thing as an indefinite double integral. If you perform a double integral and your final answer has variables in it, that is to say the variables you were integrating with respect to, you did it wrong. That's all there is to it, okay? Every time you do a double integral, you get a number. If that number happened to be some parameter, for instance, you're finding the volume of a sphere and you work that out, you should get 4/3 pi r cubed. That r isn't really one of the variables. That r is a parameter that tells you about the sphere. But, you know, if I ask you to get the volume of a sphere with radius 1, you need to get pi, not pi times something with x's and y's and stuff. So that's the biggest thing for you to catch right now, is that you do not have an indefinite integral. It is always a definite integral. Okay, so keep that in mind and we'll keep going with all the fun stuff. All right, let me show you some stuff on the iPad that has to do with this. And which window am I in? Okay, let's get it to work this time, please. Yes, it's gonna work. All right, so the title, Iterated Integrals. That means an integral and then another integral. So here is your essential idea for it. When you have a function, I'm going to use a big F here, so that its derivative with respect to y turns out to be the little f. Then we can talk about getting this double integral here, and I hit the wrong button. We talk about this integral here, and in particular the insides of it is the little f, and that when you do the integral that's on the inside, you would get big F, just like you did in the fundamental theorem of calculus in Calc 1. But you do that big F, and you would plug in for the y your upper and lower limits, and then you'd subtract, okay? Then, because that upper limit and lower limit might actually have functions of x and y involved in them, then you still have another integral to do inside of this, okay? Now, you have to understand that The outside integral here always has to have constants for the limit of integration, so that after you do the first integration, you have something with constants in it. Remember my comment earlier, there is no variable there at the end. So if you do the integration the second time and have y's in it after having had x's in it the first time, you'll get the wrong answer. And it's just that you've got problems about the setup. You'll get them. It just takes a couple of times practicing to get it figured out. So as I say here, application of the fundamental theorem of calculus. And then I need to point out to you how the setup goes here, right? So when we talk about these iterated integrals or these double integrals, they are talking about a region in the plane in here that you're integrating over. No longer are we integrating over just an interval, but we're actually looking at a region that is in the plane. Now, the inside integral that you have there, where you're doing this with respect to y, what you have to think about is that the values of x could be anywhere in between a and b. But when you are at some particular x value there, that your lower limit of integration and upper limit of integration that you've got are going to form an interval. So then if you take and change the x value, then you would change the limits. But in each case, it's still an interval. It's just an interval that happens to depend on x. Okay? So when you are setting one of these up, what I want you to think about, if it is in terms of the, if it is in terms with the y on the inside, then you need to be thinking that the y values are going to range between some lower and upper limit for that integration that is on the inside. You perform that integration, and now you'll have stuff with just x's, and your x's are integrating across from x equals a to x equals b, right? But when you set one of these up, draw your region. If you are so cool, you don't need to draw the region, bully for you. But I will ask you on every one of the homeworks to draw your region because I don't believe you. Sorry, it's hard to do these without drawing the region. Draw the region. It will help, okay? All right, anyway though, so as you go across these, you will be writing yourself an integral, and you'll just write down integral, whatever that function is inside. Maybe it's sine of x minus y, just making that up, has nothing to do with what you're integrating over. The region and the function you're integrating are not associated with each other in general, okay? The application that you put them to, and we'll look at that here in a minute, we'll say something on that. But now you're setting up this integral, and on the inside, you think about, I pick a particular x value, and I draw an arrow up across my region in the direction that y increases, because I'm doing y first. And then I would say my lower limit is whatever that g of x is there. Because I'm trying to be more concrete, maybe that g of x turns out to be x squared, just making something up, okay? And then the upper limit, maybe that turns out to be, I don't know, x plus 1, something like that. So you write down the lower limit, the place the arrow hits first, and then you write down the upper limit, the place it hits last. And then you come back to it and you say to yourself, where do my x's go between? Lower limit, maybe it's 0, and upper limit, maybe it's pi. I don't know. Just making that example up real quick there. That's how you set these up. Now your textbook will have examples that they will do, and they will start you out always doing rectangles. And I need you to understand that that is a mistake. They should not start you out with a whole section of rectangles, because most regions are not rectangles. If you assume every region is a rectangle, you will always get 0 points for that. If it's not a rectangle and you say it is, I will give you no points, because you've got to see what's going on with that, right? If it's a rectangle, then both of your limits of integration that we're seeing here, both of them will be numbers, all right? Both the y limits and the x limits, both of them have to be numbers if it's a rectangle. If it's not a rectangle, then it's not, okay? All right, we're gonna do one where we evaluate here, but I wanted to first show you a picture. I asked Don to get this picture figured out, and Jonathan Hammond gave some code that Don adapted a little bit, and I don't understand how the code works entirely. Therefore, I can't really modify it myself yet. So I'll figure it out as we go along, but for right now, let's see. Hopefully you are seeing something that's titled Slicing of a Surface by a Plane. That came from a bunch of code here, and I'm trying to find where Don put the note to change this. There we go. Don said, change this. And so I have a function in here, which is just x squared minus y squared, and then divided by 4. I divided by 4 to make it look a little bit better. So the picture that you should be seeing here has what we refer to as a hyperbolic paraboloid, or in another phrasing, a minimax. And oh, great, I'm able to rotate it so that you can see. So you can see that kind of a shape that it's got to it there, right? And the thing that is going on in this, okay, that seems like that adds too much detail to it. It makes it harder to read. But that cross section that you've got in there has this area that we're showing on that. And if I go back in here and change px a little bit, then it chooses a different cross section. Maybe I should change my px farther than that. So it would choose a different cross section for the plane there, and I get a different cross-sectional area, right? So the thing that is going on in that regard is, and if we look back at what we were talking about earlier, then the moving of that cross-sectional area corresponds to my moving with this arrow up and down, okay? And that means that when we do this integration that is sitting in here, that integration actually gets me a cross-sectional area. And then once you've got that cross-sectional area for each possible cross-section with an x value, then you add up those cross-sections, and that gets you a volume. That's what's going on with these double integrals, okay? All right, so let's see an example or two of what you'll have to do in the homework. So I'm going to take a look here at evaluating this one, all right? And I went ahead and drew the picture here, and because it says y squared dy, that means that the arrow is going in the direction of increasing y values, and it went from y equals 1 to y equals 2. Okay? And then it said, how far does the x values go after that? This time it's just a rectangle, so the evaluating should be easy. However, notice I never mentioned y squared. Y squared did not create the region. Y squared is going to be a surface that's above the region. But insofar as evaluating, you'll write down the 0 to pi, because it's on the outside, it happens last. The integral of y squared dy is 1/3 y cubed. Evaluate it from 1 to 2, and then put a dx after it. So we get an integral 0 to pi. And when we plug those in, we would end up with an 8/3 minus 1/3, or in other words, a 7/3. And then you do this integral 0 to pi, integral 0 to pi dx. There's no function in there. That does not mean it's 0. That means it's 1. When you integrate 1 from 0 to pi, you get pi. So we get 7 pi over 3 for our answer there. All right. So let me make a quick observation on that I'm pretty sure that you'll also get in Don's videos. Quick side note, make sure and watch Don's videos as well as watching my videos. Not just because you'll hurt his feelings if you don't, but because we might have hidden some extra things in there that you can only get by seeing both videos. All right, so the observation that you're going to see is, if the function that is inside can be factored into an x part and a y part, then you can break it up and say integral 0 to pi of the x part, so there's just the 1 dx, times the integral 1 to 2 of the y part, right? But you can only do it if you can factor the function. If it can't be factored, you can't do this. So keep that in mind, all right? So if we went ahead and did that first integration, we would have gotten a pi, and then that second integration, the 1/3 y cubed 1 to 2, and so we end up with 7/3 pi for our answer there, okay? All right, good enough? Now let's do the other one. Notice that on the other one, all I did was swap which was x and which was y. Now, if you do that, then that means that whereas on the first one, we drew an arrow, oh, I should draw a thicker arrow. We drew an arrow in the direction that y increased. Now we draw an arrow in the direction that x increases. The place that we enter the region is where x equals 1, and that's why x equals 1 is the lower limit. The place we exit the region is at x equals 2, and that's why x equals 2 is the upper limit, okay? All right, so let's go ahead and evaluate. I need you to notice we have a different region, okay? And so we will leave, well, okay, we can go ahead and say 0 to pi, and this time the 0 to pi, okay, this time the 0 to pi has to do with the y's, so we can pull it out like that, and then the x's go 1 to 2, and there's just a 1 dx, and so now this time we'll have 1/3 y cubed going 0 to pi, and then we'll have x going from 1 to 2, and so you end up with 1/3 pi cubed, and then multiplied by 1/2, oh, no, we don't have 1/2, what am I saying? Times the 2 minus 1. So we end up with 1/3 pi cubed. I don't know exactly what pi cubed is. It's, I don't know, going to be something like 27, 30, something in that range. But 1/3 of it will be like around 10. Whereas if we talk about 7/3 of pi, we're going to get like 7 or 8. So I need you to notice that when we swapped which was the x and which was the y, when we swapped which was the inside integral and which was the outside integral, we got totally different values because we were talking about totally different regions, okay? So the actual integration is really a mechanical process. You think about integrate the inside portion and evaluate, and once you've done that, then you can integrate the outside portion. If it so happens that you can factor this, then you can break it apart and do two integrals independent of each other. But that doesn't always happen, so be aware. All right, now let me see what was the next setup here. This one asks us to set up and then to evaluate the integral. It's going to have sine of xy across the region where x goes from 0 to pi and y goes from pi over 2 to 3 pi over 2. Okay? So because of the fact this is a rectangle, it doesn't matter what order we do this in. I'm going to write integral, integral. So I am going to write that, and let's make a copy of it down here. And we're just going to do both setups, and then we'll just evaluate one of them, okay? So doing both setups here, let's do dy dx first, right? So if we do dy dx first, that inside limit is the y's, so I need this arrow up here, like so, and it goes in the direction that y's increase. As we enter the region, y is pi over 2. As we exit, it's 3 pi over 2. If that was not a rectangle, then those would be functions of x, not just numbers, okay? Then we say, what is x allowed to go between? It goes between 0 and pi. So there we have that. Now, on the other hand, if we were to do this in the direction dx and then dy, then we would draw an arrow in the direction that x increases. X enters the region where it's equal to 0, and we exit the region where x is equal to pi. Then we say, what is our range that we're going through with our y values? Those were pi over 2 to 3 pi over 2, okay? So we can evaluate either one of these. Because it's a rectangular region, there's not going to be any more difficulty doing one than the other. So I'm going to take here and just erase the second one. And we're going to go ahead and do the evaluation. So with regards to that evaluation, we will leave the 0 to pi on the outside. We cannot factor sine of x plus y, so we have to think about just integrating sine. When you integrate sine, you get minus cosine. We would have to do a u substitution. U is x plus y. The derivative of that would have been just dy. So we'll end up with just a negative cosine of x plus y. I let this get too close up there to my picture. Let me scoot it down a little bit, right? But we're evaluating from, and I'll jot down y equals pi over 2 to y equals 3 pi over 2. And then outside of all of this mess, we'll write a dx, okay? So you probably are asking, do I have to write the y equals? No, you don't, but you have to remember it, okay? So make sure that you write things neatly and that I can tell that you mean for the y to be pi over 2 and 3 pi over 2. So plugging in here, I'm going to plug in the 3 pi over 2 and have minus cosine x plus 3 pi over 2 minus negative cosine of x plus pi over 2, and then dx. Okay. Now, we can do u substitutions on those, but again, you're masters of u substitutions, so this shouldn't be super hard. 0 pi, oh, what am I doing? I don't have to write that again. So now we have to think about the integral of cosine is going to be sine, so we'll have minus sine quantity x plus 3 pi over 2 plus sine x plus 3 pi over 2. No, it's pi over 2, silly head. Pi over 2, okay? And then that we're going to evaluate this with the x is going 0 to pi. So plug in the pi, and we will have minus sine, let's see, pi plus 3 pi over 2 is 5 pi over 2 plus the sine of 3 pi over 2 minus, oh, whoops, okay, minus a negative sign. We're plugging in the 0 this time, so it'll be 0 plus 3 pi over 2 plus the sine 0 plus pi over 2. All right, and all those are super nice numbers, so we can totally do this almost in our heads. 5 pi over 2, the sine of that is positive 1, and 3 pi over 2, the sine of that is negative 1 minus negative, and I wrote a little bit, sorry, I got a big eraser there. I meant to have a little one. It was supposed to be 3 pi over 2, and I wrote 3 pi over 3. Okay, so minus the sine of 3 pi over 2, so that's minus a negative 1, so I'll write positive 1, plus, and now the sine of pi over 2 is 1. So when I put all that together, I end up with a negative 4. Boom, done. Okay. I did way more detail than you'll probably actually need on that, I know, but talking about each individual point as we go on it, and we're just doing these integrations, all right? Okay, let's see what the next setup is here. This one, the instructions say to set up and evaluate the integral of x squared plus y squared over the region bounded by y equals x and y equals x squared. Now, please notice I have to give you both the thing to integrate and the region. Those are two separate objects, okay? But we're going to set up for this and integrate. Because it says y equals x and x squared, I suspect that I'll just take my function and integrate dy dx. I might be wrong, but because it said y equals x and y equals x squared, that's kind of my suspicion, right? So setting up my limits of integration, I'm going to draw an arrow that goes in the direction that y's increase, that is to say, up. And I'm going to say I enter the region where y equals x squared, and I exit where y equals x. And then keeping in mind that this arrow could have been anywhere in my region, then I will say my x values ranged all the way from 0 to 1. Okay. Now we evaluate it. So evaluating it, notice that we could not factor. So we have to think about what's the integral of x squared with respect to y. Well, that's just going to be x squared y. And the integral of y squared with respect to y would be plus 1/3 y cubed. We will have to evaluate from x squared to y squared, and then have our dx after that. So evaluating here, we still have the integral 0 to 1 hanging on, and we're going to plug in hey folks, I wrote something weird here. That was supposed to be an X. That was just an obvious copying error. Because if you notice, it's just going from here to here, and I turned it into something completely wrong. But I fixed it. Now we're going to plug in y equals x, and we will have then x cubed plus 1/3 x cubed, okay, minus, now we're going to plug in the x squared, and we'll have x to the 4th minus 1/3 x to the 6th dx, okay? So this is an integral 0 to 1, and we've got what? 4/3 x cubed there, and then minus x to the 4th, and plus 1/3 x to the 6th dx, okay? So we would have 4/3 times 1/4 x to the 4th minus 1/5 x to the 5th, and plus 1/3 times 1/7 x to the 7th. We're going from 0 to 1. Fortunately, 0 and 1 are super duper friendly numbers. And so we'll plug in the 1 there, and we will have 1/3 minus 1/5 plus 1/21 minus, and then when we plug in the zeros, we get a bunch of zeros, okay? So that there ends up being, gosh, I don't know, 2/15 minus 1/21. I'm sorry, I can't do it in my head, but you can whip out a calculator and do that. Please notice that it should turn out to be a relatively nice fraction. So, you know, give a fraction as an answer. You don't have to have a decimal for everything. If what you wanted was a decimal, then you could have just at this point right here, plugged it in your calculator and just let it give you a decimal. So, all right, I think there's one more example, and then we'll roll on. Actually, let me check to see. Yeah, this is the last example here. So this is a type of problem that you will see crop up again and again, and you need to see the trick of it. If there wasn't a trick, you wouldn't have to do this problem, okay? The reason that you have to learn this trick is sometimes you run across integration that you cannot do. The integral cosine of quantity x squared is a special function, and until we were in the habit of using computers for our evaluation stuff, we had to like write tables for this kind of crap. I'm sorry, this kind of super interesting stuff. Haha. But seriously, this sort of thing was being done at the end of the 19th century, but everybody looked it up in books and copied numbers out of books and stuff like that. Or at worst case, you had specialized equipment to actually figure something out as you went. People went to the moon on slide rules, I'll tell you. We ought to be accomplishing a little bit more, I think, with the technology we've got right now and that kind of thing. All right, so as mentioned, integrating cosine of x squared dx, there is no u for a u substitution, so you actually can't evaluate this. You have to change the order of integration in order to make it possible. When we do change the order of integration, we will generate a u substitution. So it's going to get better. So as we do this, the function inside does not change. But now we will do this dy dx instead of dx dy. And so once the inside part says dy dx, now we have to think about drawing an arrow in the direction that y increases. The direction that y increases, of course, is up. And now the lower limit of integration is y equals 0. The upper limit of integration is y equals x. I'm not sure if it came through on the mic, but somebody in the neighborhood does not have a muffler. So, all right. Once we've got the limits going 0 to x there, then we just have to say to ourselves, where does x go between? And x goes between 0 and 1. Once we have that set up, because of the fact that we need to integrate cosine x squared with respect to y, all you end up doing is getting a y that goes from 0 to x, and that means that you have an integral 0 to 1 cosine of x squared times x dx. Remembering the sort of thing we did in Calc 1, our u is going to be x squared, our du is 2x dx, which means 1/2 du would be x dx. So this integral becomes the cosine of u times 1/2 du. But then we have to say, okay, if x equals 0 and we plug it in here, what do we get? Well, we get that the u is 0. And if x equals 1 and we plug it in here, what do we get? Well, we got 1. Let me emphasize here that that was u equals 1 and u equals 0. If the, oh, holy crap, guys. If the limits had not been 0 and 1, which they weren't, then that would have changed the problem. Oh no, Ben has to go back and fix it. Do y'all see what I did here? This is making me feel bad because I have all of my limits of integration done wrong. And it is just because I wasn't paying attention. Nope, I'll tell you what, it was totally because that guy who needs a muffler drove his car by, totally distracted me. All right, what did we say? Lower limit would be y equals 0, upper limit would be y equals x. So that part actually didn't change. Our x's went from 0 to the square root of pi, okay? And then we still had the 0 to x here and 0 to the square root of pi. Okay, and now it's at this stage when we plug in x equals 0 and we get u equals 0. And x equals the square root of pi, and we get u is equal to pi. And so now we have 1/2 hanging out front. Integral of cosine is sine u, 0 to pi. And then we have 1/2 sine pi minus 1/2 sine 0. Oh man. So at the end we get 0 out of it. That felt a little bit dissatisfying, but you know, sometimes they do. All right. So iterated integrals, it's just integrating two integrals. The inside integral is going to end up having variables in the limits of integration sometimes, and you have to just plug those in. The outside limit of integration never, ever has videos. Has videos, never has variables, okay? So as you're going along, if you have variables in both those limits of the inside and the outside, then you're not doing it right. Set up on these, the inside will have variables if it's not a rectangle, and the outside will never have variables, okay? All right, that should get you going. Go do some of that homework.